Good? Okay. Welcome, everybody. Good to see you here again today. As you know, I'm Glenn's sister, Rebecca Berman, and I'm honored to moderate today's session again. And your loved ones continue to be safe and well. Cannot believe a week has gone by. Here we go. Glenn Grossman is an epidemiologist with over 20 years of experience. While pursuing his doctorate in epidemiology at UNC Chapel Hill, Glenn served as an epidemiologist on staff at the UNC Infectious Disease Clinic for 2 years and taught epidemiology and advanced analytics at Duke Medical School and UNC. He has been involved in epidemiology projects with Medicare, Medicaid, Veterans Health Administration, Military Health Service, CDC, and other programs in the United States and outside of the United States. He is currently Senior Director of Outcomes Research and Epidemiology at Novartis, but all views expressed today are his own. So Glenn, thank you for sharing your time with us again today to give the audience a kind of a preview of the questions that have come in this week and some of the topics Glenn will be covering. Glenn will be talking about what's happening in the different states around the country and who's opening up when and what's the status locally. What are the risks of getting COVID-19 from going to a swimming pool? How effective are masks? We'll be talking about the vaccine and a bunch of other really great questions. So thanks to everybody who sent in questions during the week. And without further ado, I present you Glenn Grossman.
Thanks, Becky. And thank you very much for moderating again this week. I really appreciate it.
My pleasure.
So go ahead. What's the first question?
Okay. So the first question we have for today is, what are COVID-19 neutralizing antibodies and how are they different from other antibodies?
All right, this is a good question. All right, so here is the issue. Let me make it a little bit bigger. Oh, that's too big. All right, so there's different kinds of antibodies. And so normally it doesn't matter so much whether it's a neutralizing antibody or not. The problem is, with this disease in particular, there's a subset of diseases out there where this becomes a really big issue. It was noticed in dengue fever and noticed in SARS-CoV-1, so in the first SARS around 20 years ago. And so a normal antibody is like a flag. And so it will flag a part of the antigen or the cell or whatever it is that it's linking onto. And it will activate typically the rest of the immune system with this flag so that the rest of the immune system knows to target it and get it out of the body. With a neutralizing antibody, the antibody actually goes to the place where in this case, let's talk about SARS-CoV-2. So with SARS-CoV-2, we know that it binds with the ACE2 receptor. I can use my mouse. And so if the antibody binds directly to where it would have bound to the receptor and prevents it from binding, then this is called a neutralizing antibody. So it's not just an antibody that links anywhere with SARS-CoV-2, but it particularly binds to the place where it would have where the binding site for the ACE2 receptor. And so it physically prevents it. Even if there's no other immune reaction, the antibody itself prevents the binding with the ACE2 receptor. That's good because that's not just a normal antibody, this is a very specific kind of antibody. We're finding a potential problem though, and that is if there's a non-neutralizing antibody that doesn't flag on, then normally what happens is that you have these monocytes and macrophages, these other cells in the body that go and attack the whatever the antibody is clinging to. And what we're worried about with SARS, that we identified with SARS, and what we're worried about with SARS-CoV-2 is two things: that these non-neutralizing antibodies might actually take SARS-CoV-2 and make it easier to get inside of this monocyte macrophage and then actually infect monocytes and macrophages. So then this becomes a cell for replicating. So then you see over here that you might have some replication going on inside the macrocytes and rather macrophages and monocytes. And so this is really bad, because then what happens potentially is that we just don't have to worry about ACE2 receptor binding. Now we have to worry about replication going on here too. And another thing that could potentially happen with non-neutralizing antibodies is that you might get it also brought into the monocyte macrophage cell again, like you did before, but then even if it doesn't replicate like before, you might have an excessive, exaggerated immune response based on the pro-inflammatory cytokines and the and sort of the cytokine storm that we might be sometimes talking about. And so this was found in SARS. It was found in dengue fever. It's potentially worrisome, because this is if we end up creating vaccines that create non-neutralizing antibodies, then what's going to happen is that potentially people could get really sick if they get infected with SARS-CoV-2 after taking the vaccine. So it could be the case that the vaccine is even worse than no vaccine. And that's actually what happened with dengue fever. I don't know if the lawsuit was resolved with, I think Sanofi was one of the folks making the vaccines for it, but it turned out that, so with dengue fever, people can get reinfected more than once. And so it's problematic. And so people need to, so there was a vaccine developed to prevent severe complications if they were infected more than once. What they found out with this vaccine was that people who are never infected with dengue fever actually had worse outcomes if they had the vaccine than no vaccine at all. So it was good for use with people who previously were infected, but not for use with people who are never infected. This is something we're gonna have to pay attention for here. And the problem is there are so many vaccines being developed all around the world, there might be different standards. And so what's going to be really, really important when we hear news about the vaccines coming out is whether it's a neutralizing antibody or just antibodies without referencing to neutralizing. Finding neutralizing antibodies takes a lot more time and resources and effort, because it's not a standard antibody test that we're doing. One more thing that leads us to suspect, so we don't know for sure if this is going on. I think there's still a debate. There might have been more research on this over the last week or two that I haven't noticed yet. But one of the early things that we saw was down here, that people who had higher amounts of antibodies in their body earlier tended to be the ones who had more severe outcomes in SARS. And so this is what we're worried about here with SARS-CoV-2, that it could be that the antibodies themselves, it's not just ACE2 receptors that we have to worry about, those cells. It could be that the cell is that the virus is replicating in our very immune system. And so we need to pay attention. I think that's it for this topic.
Okay, thank you, Glenn. So basically, to summarize, am I getting this right, that we're looking for a neutralizing antibody?
Right, and so it could be worse. So what are we gonna do if China or another country announces that they have a vaccine and it creates antibodies, and they release it to the public and say, look, we have this vaccine ready. People are gonna hunger for this vaccine. Everyone's gonna wanna get their hands on this vaccine. But if it turns out that we don't know if it's a neutralizing antibody vaccine and that it's actually not making enough neutralizing antibodies, even if 1% of the population gets these non-neutralizing antibodies that potentially cause these adverse effects, the antibody-dependent enhancements, the ADEs, this could be severe when you're talking about potentially billions of people getting a vaccine. So this is potentially, because everyone's going to want a vaccine. When it's first announced, we're not going to care if it goes through the FDA. If we hear that some other country created a vaccine, everyone's going to hunger for it and want to get their hands on it, but that could be problematic. All right.
Okay, good to know. So what's the status with this vaccine or any vaccine or one that we want? Where are we? How long is it going to take to get to this vaccine?
So the last time I checked, this was from a couple of weeks ago, there are, well, so it's not the way that the vaccine is created, rather. Instead, it is different vaccines create different antibodies. And so that's just something for people to know. There's different antibodies that are created. So we think about one antibody for SARS-CoV-2, but in reality, there could be a huge number of different antibodies. Different people are creating different antibodies for the same virus. depending on the binding sites, depending on slight mutations. So there's a huge diversity of antibodies. There's lots of different ways to create these vaccines, and I don't know if any are better than others. Some of these might be more specific, and if you made a more specific antibody from a vaccine, and that antibody was almost 100% or 100% of these neutralizing antibodies, then that would be good. So right now there's a variety of different approaches that are being used. Moderna, for instance, that you might have heard about in the past week or two, was an RNA vaccine, a messenger RNA vaccine. There are some others that people are talking about. But yeah, in terms of the timelines, let's use this to talk about timelines. So normally, I'll put here, normally the majority of drugs and vaccines that are tested fail to come to market. So for every 100 drugs or vaccines that are tested, typically only 5 to 10 actually make it to market, probably closer to 5. And so that means that right now we're starting to hear from some vaccine trials that they've passed phase 1. Well, phase 1 is very, very small. It's typically a very small trial where they look at things like dosing. They might begin to look at things like safety, but it's typically too small to really have a good sense of what's going on. So that those types of issues typically come and are looked at in phase 2. But phase 1, typically only 1/3, or so 37% fail. So we're going to expect that the vast majority of these vaccine trials are going to pass phase 1. But just because they pass phase 1, it doesn't mean that they're going to actually make it to market. Over 80%, roughly 85%, et cetera, will make it to market, or rather will fail to make it to market. The vast majority will fail. And so we know that because there's so many that are being investigated, it's like rolling the dice over and over again. So we have high confidence that some will be ready, but we don't know which one in particular, when, or whatever. If you look up here, here's how long it took to create some other common vaccines that you might be aware of. So for the varicella vaccine, it took 28 years. Flu mist took 28 years. The HPV vaccine, 15 years. COVID-19 goal, as we're looking at, is under 2 years. So you see that this is not something that as a typical process. In fact, just to give you a little bit more detail about this. So the typical process would start with academic research. You could see might take 2 years just on that alone, just to identify a vaccine candidate. This is before you even start doing the clinical trials and these kinds of things. Then once you do this, you might do some preclinical trials in animals and in primates or in mice or in other animals to try to see what it looks like in organisms. That typically takes a couple of years. Then only after these things are complete, then would you go ahead with the phase 1 trial. After phase 1 is complete and you know that you're not going to hurt anyone, then you go on to phase 2, because phase 1 again is dosing and that kind of stuff. Then when phase 2 is over, then you have enough confidence to go into phase 3 and you go forward. All of these are done serially, one after the other. And in particular, building factories itself, you can see, takes quite a long amount, a huge amount of time to do. And then in terms of manufacturing, approval, these other things, it typically takes a huge amount of time to demonstrate safety and efficacy. And you need to, particularly in vaccines, because they're typically given to people who have no illness at all. And so you need to ensure that they are safe and that they are effective. The problem here is that in order to get a vaccine ready for 18 months, it's going to require the timeline on the left, where essentially we're scrunching everything way down. So the academic research, instead of it taking the normal 2 years, we've scrunched it down to just a short period of time. The preclinical trials. So the phase 1 trials, Moderna has already passed this phase 1 trial. It was only in like 45 patients. So the order of magnitude, not a lot. These other vaccine trials also, because they're rushing ahead, it's going to be in a small number of patients. And then you can see that phase 2 and phase 3 trials are going to be started. Some of them are going to be concurrent rather than serial. And so the worry there is that if there are safety issues identified in phase 2, you won't even know. You'll have already started enrolling people in phase 3. Another thing, so these phases of trials, typically they're sort of like getting your feet wet, the first trials, just to make sure that, to look at that there's no huge safety risks or other kinds of things before you potentially put a larger pool of patients at risk in phase 2. And similarly with phase 2, you would give it to a lot of people, but you wouldn't give it to a ton of people in case there are some safety issues that are identified. But then when you're studying, if you get confidence that it came out okay, then you would do phase 3 with a lot of people before you would then start preparing for launch to the market. If we're here starting to enroll for phase 2 and phase 3 at the same time, then all these people in phase 3 are potentially at risk. And so this is worrisome, and particularly because we know with SARS that this question of these non-neutralizing antibodies was such a big issue. This is something that would concern me a lot in terms of looking at this, because say you have an outcome, a safety outcome, where it only happens to, let's say, 1 in 100 people, so 1%. Well, if you give this drug, the vaccine, to 1 billion people, you are talking 1% of 1 billion is quite a lot of people. And so this is really this is the risk. By accelerating the timeline, that is the risk of what could happen to us, and it's very worrisome. Because we know what to look for in terms of neutralizing antibodies versus non-neutralizing, it's unlikely that we will be launching vaccines with the non-neutralizing, because we're going to be paying a lot of attention for it, but there is still risk there, and that's something that we need to be aware of. The other risk is more of an economic risk. So in order to hit these timelines, we're going to have to start building the factories now. In fact, I think some of the factories already are being built. And the type of infrastructure you need for one vaccine is going to be a totally different infrastructure than you would need for another vaccine. So we're building all these factories now to get the capacity up there. But if the vaccines end up failing, we will have invested all of these millions of dollars in these factories that we can't actually use. And so the economic risk, I think everyone agrees that's okay. It's a cost we need to do, because there's no other way to get to August 2021 unless we build these factories now. But we know that there's also this economic risk there. But for me, that's the small risk. For me, the safety risk is the bigger issue that I'd be worrying about. And that is that.
I know you don't typically talk about necessarily individual drugs that are being developed. I know we have a question about the J&J drug. I saw in the news something about a drug being developed in Oxford. Is that phase 3? Are many of these drugs that you mentioned earlier, what percentage have made it to this phase 3?
So okay, the ones I mentioned earlier are only vaccines. There are a lot of trials that have made it to phase 3. So the question is, among drugs that have already existed on the market, like, so for instance, when you look at the, I think I had a slide here. When you look at the tests for the malarial drugs, so these are late phase drug trials, in the sense that they've already been shown safety and efficacy for other indications. And so they're already late phase trials, but they're being evaluated for this new condition, COVID-19. Previously, this was a contender. Now, some of the most recent results are indicating that generally these anti-malarial drugs should not be used for most people for treating COVID-19, because rather than preventing death, they actually make it more likely that people will die if they take it. So it's not even that it's a neutral thing, it actually makes it even worse for people who have COVID-19. So people who have COVID-19 should probably not be taking this drug. But so in terms of the vaccine, so I shared with you this slide like a few minutes ago, which was looking at the total number of vaccines, but that doesn't include the total number of drugs. So there are a lot of investigations. I don't know the order of magnitude, but there are many, many, many. If this is just the vaccines that we're looking at, let me see if I can find this again.
While you're looking at that, so the question is, so another question that came in is it more likely that we'll have a treatment drug in place before we have a vaccine?
Oh, that's a really interesting question. So the order that I'm looking at in terms of, I think that there are 5 or 6 interventions that we can look at. And I'll try to do it in the order of how quick they'll come to market. The first is test and trace. We already have that capability up and running. Obviously, it's more advanced in some places than in others, but it already is a capability that exists. So test and trace is first. With test and trace alone, without anything else, we could end this epidemic. And so that everyone has to internalize that just by test and trace, we could start opening up society again. Once the number of new infections gets to such a low number that R gets below 1, we can have high confidence that there's so little virus circulating around that we can get back to mostly normal with only test and trace and no other intervention. So people need to know that. And that's already starting to be executed. But this is a big issue. That's why so much, from a public health perspective, so much early interest has been in test and trace, because test and trace is every bit as effective as a vaccine in ending an outbreak. And so that's why there's been so much talk about it. Test and trace is first, and so there should be more money put into that. The second, I would say, is these repurposed drugs. So as we identify drugs that were previously studied for other indications, remdesivir was an example, these intramolaros, there's a bunch of other things that are being investigated, then we'll see those results next. And so we've already started seeing some of those results, as you can see, and those we're going to continue to see sooner. After we have repurposed drugs, the next that we'll get most quickly are repurposed vaccines. So there's a bunch of trials that are being evaluated for vaccines that were used for other therapeutics, for other indications rather. The first set of vaccines that were looked at were for the BCG vaccine for tuberculosis. We've also been looking at polio, we've been looking at the MMR vaccine, because each of these vaccines, in addition to generating antibodies, also seems to stimulate the innate immune response and might just have an overall protective effect against respiratory viruses. So they're also being evaluated. If there's a positive result there, then we'd find that next. Then after that, the very next thing that we'd probably find are new, either new drugs or new vaccines. In terms of the order in which they're looking at, people are racing to identify both. So both identifying vaccines and racing to identify new drugs. And so the vaccines that we're talking about here are very specific. And so it would be completely new vaccine that never existed in the world before. Similarly, I would also say these new treatments that never existed in the world before, specific to COVID-19. These are what are going to take longer, and for the primary reasons that I said, because safety with pre-existing vaccines and pre-existing therapeutics, you already have a good sense of the safety profile, so you can rush ahead much faster. With new drugs and new vaccines, you don't know the safety. And that, let me go back and stress this again. This is why drugs cost so much. This is why it takes so long to get a drug to market, because of this one graph that you see on your screen. The vast majority of drugs and vaccines that are investigated for launch, the vast majority of them fail. And so because of this, the reason that they fail, sometimes they fail for efficacy, and sometimes, and so let me say even more plainly. So these drugs, these candidates that we're evaluating, it's only ethical to investigate them in people if you have a really strong scientific basis for believing it's going to be the next cure for the disease, or it's going to really reduce the burden of the illness. If you don't have a basis for that, then you wouldn't even test it. So every one of these drugs that fails and has gone through these trials, we all thought that they would be the next best new, the greatest thing since sliced bread, and they all fail. And let's say 95% of them fail. And so this is just the way it is, and that's why it costs so much to develop these drugs, because you have to spread the cost around all of the failures in addition to the successes. And so that's why it takes so much time. That's why it takes so much money. And so it's an important concept. All right.
One of your slides, you mentioned August 2021. We have a question. What was that? What were you indicating there?
This is 18 months. So what would we need to believe if when people were announcing 18 months in the future would have a vaccine in order to get to 18 months, so August 2021, what benchmarks, how long would each of these components need to last in order for us to hit that milestone?
Compared to the graph on the other side showing how long it all takes and having it.
So this would be more typical, and this is if we try our hardest at every single stage and everything goes exactly right.
Got it. Okay, so you mentioned test and trace. We're relying heavily on that now that states are open, yes? Where are we with test and trace? Let me see, where is the question? And do we have enough tests being done? Do we have enough tracers in place? How do we know? Is there sort of a central database? I mean, where are we getting this information? And do we feel that we can really rely on this to be a tool that will be effective?
Good questions. All right, so first I'll start with testing. This is a little bit dated at last, as you can see. This is from May 14th that I pulled it. I didn't get a chance to pull it this week, but so these numbers have gone down some, but they're representative. So what you can see, what we're looking at is the percentage of tests that were positive. And so ultimately, in what we should aim for is to get the positive test results, the rate, down below 5%. Because we know that the percentage of people with active infection is well below 5% in almost all cases. Because even during the outbreaks that we were having, 5% was roughly what we were hitting in some places. In the vast majority of places, it was well below 5% in terms of people at any point in time who had a new case, a new active infection. And so when you see these big numbers, like in France, 15.9% as of May 5, Netherlands, 15% as of May 13th. When you look at these big numbers, what it means is that they are not doing testing on a wide enough basis. Instead, what it means is that the patients who are getting tested are the ones who already have symptoms probably and are more likely to be positive. And when we talk about test and trace, you can't just give tests to people who are symptomatic or who want to have tests. You need to give it to a much larger group of people, random testing even, because that's the only way that you will have a wider net to be able to capture all the people who are potentially positive. And so that means once you start getting numbers down to 2%, 1%, then you have a good handle. Then it's under control, because then any new infection you're very, very likely to get, or to catch rather. Any new infection you're very likely to be aware of with this test. And so this is a really good indicator whether there's enough testing going on. This is outside of the United States. You see the total in the United States as of May 13th was still 13.7%. Again, this indicates not enough testing has been going on. When you look specifically at the states, again, this is a little bit dated as well. This is very dated. New Jersey's come down quite a lot, but at one point it was 32% of the tests were coming back positive. We really need to get all of these numbers down to below 5% in order for us to open up. Some states are opening up, which we can get to a little bit later, despite not meeting this metric, which means that their contact tracing and their testing capacity is not where it needs to be, and people are going to get infected, and there's going to be chains of infection that will not be caught because not enough testing is done. But right now, this is the best metric we have to see whether enough testing is being done. Oh, for contact tracing, so there's some models that are being done. This is, I think I just updated this recently. And so based on the number of, the prevalent number of cases, this is the contact tracers that you would need at a state-by-state level, aggregated at the United States level. We're looking at almost 200,000 contact tracers, including the contact tracers themselves and the supervisors needed. We know what the structure needs to look like because we've been doing contact tracing for years in public health. So for instance, for STDs, for HIV, for other things like that, the infrastructure and the capability and the understanding has been around for decades. So we know what best practices look like here. And so in terms of calculating and estimating the volume, then we have pretty good estimates. The problem is going to be if there is a local outbreak where there's more people that get infected that overwhelms the local system, then we would sort of need surge capacity in that area. And so we should invest in sufficient contact tracers and testing capacity to ensure that even if there's a surge, that we can still jump in and meet that surge level to identify everyone and get the chains of infection under control. And so the more we invest in this, the less likely an outbreak will happen. If local outbreaks happen, then we're gonna have local lockdowns again in those areas. And that's what we might see in the fall and winter when things get bad again. Go ahead.
You explain the different color shading on this graph. What does that mean?
Yeah, absolutely. So what's represented here is basically how many cases there are by state. So some states right now don't have very many cases at all. They're lighter. Some states like New Jersey and Massachusetts and Illinois, these are very dark and these have more cases. And if they have more cases, that means you need more contact tracers, because for each case, you need to identify all the people they might have come into contact with before they were infected, after they were infected, to make sure you get the whole chain of infection and stop it. So the darker it is, the more contact tracers you need. And in fact, that's one of the reasons that we had these lockdowns, is that once you're under lockdown and you can get the numbers under control, hopefully New Jersey, once we get to a lighter color in another couple of weeks, another few weeks, then we can break the lockdown. We won't need as many contact tracers to keep it under control because there won't be as many infected people. But if this is saying the point of this is to say, we could break the lockdowns across the entire country right now and be okay if we had this number of contact tracers. Even with all these people who are sick in New Jersey, hypothetically, if we were to just conceptually think about this, if you had 1 million contact tracers and sufficient testing capacity, you can open today and just find all these chains of infection and then just stop it, even with all the cases, as many as there are right now. The problem is that would be prohibitively expensive. You'd still miss some, it would take a while, and more people would still be getting sick and be put at risk of death. That's why we're under lockdown, to get it more to a lighter color. But literally, we could open up today if we had sufficient capacity. So basically, when we open up, all relies on when we have sufficient capacity for testing and tracing for all of this. That's all it is. Some states, even the light ones, they might have many less cases, so they don't need as many contact tracers. But even though they don't need as many contact tracers, they might still not have enough because they're not investing enough in it, even if they only need dozens. And so the problem is they might still not be ready to open up because even though they don't need as many, they might not have as many, even at that small level. So I can get more into the details if you want about what states are opening up and whether they're ready to or not.
Tell us more about these states that are opening, and are they ready to reopen, and are those same states that are ready to reopen the ones that are opening?
All right, that's a good segue. So, all right, so here are what the U.S. federal government proposed as criteria for that we would need to meet these criteria in order to open at a state-by-state level. And I think that these are generally at a high level decent criteria. So basically, the questions at a high level are the symptoms and cases decreasing over time so that they're more manageable? Can the hospitals handle the load? And is our testing robust enough? If you look at these three things, then these are good indicators that we're ready to open. It wouldn't, obviously it's not just testing, but also tracing. But if you have a lot of testing, then you're probably have your infrastructure up enough to deal with other things. So if we look at this, there's a great website, COVID exit strategy is where this comes from, that has scored each state based on whether they're trending poorly, making progress yellow, or trending better. Right now, there's only 2 states that are trending better that should be opening up, and that's New York and New Mexico look pretty good. The other states are bad. In fact, some of the ones that are really in poor shape and should not be opening up, you can see, are in the South. And when you look on the right, this tells us which are reopening and which have maybe parts of the state that are reopening, if not the whole state. The light blue is is reopening soon, and the yellow is shut down. So you can see a lot of states are still shut down. Yellow is New Jersey. You can see, what is this? Illinois is still shut down. But you see over here, a lot of states are reopening or have already reopened now that are blue. When you see on the map, they have not met these criteria. So this is problematic. Clearly, the federal government is not talking to itself, and these states should not be reopening, given the metrics. And so if we look at a state-by-state level, this is a little hard to read. Maybe I can zoom in a little bit. But so basically, when you go down the list, so for instance, Alabama, their cases are increasing. It's not decreasing. So the epidemic hasn't sort of plateaued and then come back down to a manageable level. Rather, it's increasing. A lot of these, when you look at Arizona, Arkansas, look at it's been increasing. In some ways, the states that are opening earliest are the ones that just don't seem to care and are the ones that are least ready to open, which is a terrible correlation to see, but it is what it is. In fact, I'm not going to get too much into JP Morgan unless someone wants to know, but there was a terrible analysis by JP Morgan a couple of weeks ago, or this past week, and looking at the lockdowns versus the infectious rate after, and they totally missed the ball on this one. In the US, the ones that are reopening are the ones that are least ready to reopen. And so it's really, we're in bad shape. But generally, you can see the ones abroad, when you look at countries abroad, the lockdowns have worked. So when you look at the rate of infection, and then there's a delay in terms of the cases and the symptoms that are actually reported, when you look country by country, the R values have gone down dramatically. So when you had the initial R of maybe 2 to 3, you can see that the lockdowns worked. They reduced R below 1, and then reduced it eventually to we're not 0 in these countries yet, but we're approaching that level. You can see in these cases, we're in United Kingdom, we're not quite at 1, but we're getting there. The trajectory is great. In Germany, same thing. We're approaching 1. We've been around 1 for a little while, but the lockdowns have worked. We've reduced it from an exponential growth down to either below 1 or just a neutral 1, where for every new infection is replaced by a new infection over time. So hopefully we'll get that down to below 1 soon. But we stopped seeing exponential growth. The lockdowns have worked. The market is not reacting the right way if they don't believe that the lockdowns have worked. So I can go into more details about specifics at a later time if you want. But for now, I mean, there's no controversy in the data that the lockdowns have worked.
Speaking of controversy, though, the data is not consistent state by state, right? It feels like we've been hearing a lot this week about how some states are combining the results of the different tests that they're using, the antibody test plus the actual test for the virus.
Yeah.
About what that means and how we are able to analyze this data appropriately?
Right. So that is really problematic. There's a debate among epidemiologists about whether it is diabolical or whether it is just an error. Is it wrong or is it a deliberate malfeasance? The problem is that a viral test, an antiviral test, demonstrates whether you have an active viral infection at the site in which you've taken the sample. An antibody test tells you if you've ever had the infection, whether it's active or not active. So what we need for test and trace is only the viral. We need to identify people with active infections. So the antibodies are irrelevant. The antibody tests are good for other things, for surveillance in general, for lots of other things. But in order to identify people with active infections, that is a viral test that we need in order to identify these people. And the problem is that by scoring states, by looping the antibody tests with the viral tests, and the antibody tests in some ways can be cheaper and easier to manufacture, then you're almost gaming the system and making it seem like the states are ready to open up, when in fact they're not ready at all. You're just gaming the system and making it seem like you have more tests available, when really there's not enough tests available, because you need to be identifying active infections. The only way to stop the outbreak is to identify and lock down the active infections. And so a few states were doing this, which is bad enough, but then the US CDC started doing it, where we realized that they had been doing it. And that is a first year epidemiology student would realize that that was inappropriate. I mean, hopefully people on this video call realize that this is inappropriate. And I don't know whether it was trying to game the system in order to encourage states to open up before they would have really been ready, or whether everyone's just under so much stress and these people working on the public health front lines just didn't realize. Maybe it was just some very junior people who were on the website doing this stuff and they were just overwhelmed and didn't realize what they were doing. I don't know what their motivation was. All I know is that it is devastatingly bad to use a primary metric that we have in terms of whether states should open up and to almost game it by using the wrong data that you're entering into it. That's just my perspective.
I like your use of the word diabolical.
Oh, there are other diabolical things going on with the CDC that we can get to in a little while. It's really disappointing. And again, I don't know if it's diabolical or just
Essentially,
they don't know what they're doing. They're under stress. I understand they're under a lot of stress. They're working on the front lines. I can't imagine being under that much stress, but they're getting things wrong that they're the US CDC. They haven't gotten stuff like this wrong before. It's this administration that this is all new, that we're seeing them really fail like this. So many things, it's one after the next. They're still doing lots of great things. They're producing reports. They're still doing some great things, but there's so much that they're failing on. It's in some ways almost become a propaganda arm of the federal government, and it's really disappointing.
So now we all know, when we look at the numbers, now we know to make sure that the data only includes the test for the virus and not the antibodies. So thanks for clarifying that. Okay, so one of the next question that came in is, how effective are masks at preventing spread? Now that so many of these states are open and will be opening even more, and we're all told wear masks.
Yeah, so I love this video, or this was a video that I saw online by one of the makers of the masks, and looking at imaging. I think this is thermal imaging. So typically when you exhale, you have warmer breath, so you can visualize it using a thermal camera. And you can see that the mask is very effective at from air, like this bolus of air that's projecting out. The problem is a lot of people who are not used to wearing masks, their glasses might fog up. And that's an indication that there's not a good seal around the edges. For it to be effective, you need all the air to pass through the filter of the mask and back both ways when you're breathing in. If the masks aren't tight enough, then they're likely to be leaking out the sides and whatever. The interesting thing is that what we found is, despite that, simply just wearing a mask, even if it's a cloth mask, even if it's not perfect, is still quite effective at preventing transmission. So most people should be wearing masks when we go outside. Even if we have no fear for ourselves of getting infected, we could be asymptomatic and could be infecting other people. And so everyone should be wearing a mask just for etiquette, to prevent infecting anyone else, or a chain of infection. Because you might be around other people and the whole group, there might be not a high amount of risk, but some of the people that you're with, they might have people living at home who are over the age of 70 or who are at higher risk. And so you might be part of a chain of infection where people might die because of your decision not to wear a mask. So it's so important that we all be wearing our masks when we go outside.
So one of the times, though, that we won't be wearing masks is when we're swimming, right? I love how when they said beaches are open, but you can take off your masks if you're swimming. So can you talk to us a little bit about swimming pools and oceans and the risks of getting, becoming infected by going to these places?
Yeah, so there's different levels of risk tolerance. Depending on the swimming pool, depending on where it's located, how many people are in it in particular, there is some risk depending on the age of the people, et cetera. What Arkansas just reported, I think this was in the last day or two, that there was a swim party there and multiple people were infected with coronavirus, that there was exchange. We can maybe get into the question of super spreaders in a little while if you want, but this was the largest one I saw in Jordan, where there was a wedding and one person infected 76 of the 350 guests. So this question of super spreaders. If there's super spreaders in the swimming pool with you, it dramatically increases your risk of getting infected. But here are some other things to think about. I mean, so I'm not aware of any evaluation specifically looking at risk in swimming pools, but here are some other things that you might want to think about. So there have been a trial or two looking at the viability of the virus under UV light. And so they found that the quantity of UV light that you would typically get in the summer months is, they found that 90% of the infectious virus was inactivated every 6.8 minutes. And similarly, in the winter, the comparison was that every 14.3 minutes it was inactivated. This was based on dried saliva. It might have a little bit different interpretation versus people who are actively breathing and it's not saliva, but it's droplets that are coming out, versus if someone is sharing a cup or other kinds of things where saliva may not have dried out yet. But you can see that if you want to be the most safe in terms of the UV light component of it, so this is not talking about heat or humidity or other things that might be associated with the reducing the viability of the virus, of catching the virus. Then from this graph, you can see, okay, it looks like between the hours of 10 o'clock and 2 o'clock, those look like the peak times during the summer where the UV light is the best. I mean, those are also the sunburning hours. So think of the sunburning hours as the best hours to also kill off the virus. There's been more work that's been done recently looking at the seasonality, the impact of weather and climate on the reproduction rate. And what we found is that, so if our current thinking is still that the reproduction rate on average is around 2 to 3 people infected for every one person that gets sick on average. Some people are going to be super spreaders and some spread more. Some people are going to spread less. You can see that in the summer months, so summer is June, July, August, you can see that the numbers are down here. We were coming out of February, March, April, where the numbers were here, but we expect that whatever these numbers were in February, March, April, that the numbers are going to be even higher in the winter months. So we're talking about November, December, January, February, this time period. That's one of the reasons a lot of us think we're going to be hit very hard come fall. But you see there is a little bit. It's not enough to reduce it below 1. Remember, this 1 is this magic number. If you reduce the reproduction rate below 1, then the epidemic will just end on its own over time. But anything above 1, you still get exponential growth occurring. And so that's the evidence we have for, the one other thing that we've seen is there's some evidence that vitamin D might protect from critical illness from COVID-19. There's correlations, there's some trials that suspect that indicate that there might be a relationship between respiratory diseases and that can be stopped by vitamin D. Again, a lot of this is correlation. It hasn't really been investigated a lot for COVID-19. There's a problem with taking vitamin D. It's been looked at in a lot of therapeutic areas, and lots of big studies have occurred, and almost all of them have demonstrated that vitamin D is not protective. And so the correlations have tended to show, just the correlations part, not the clinical trials, the correlations have tended to show that for a wide variety of illnesses, people who have those illnesses tend to be deficient in vitamin D. So because of that, we thought, oh wow, if we just give them more vitamin D, then that would be great. We can stop these illnesses or prevent these illnesses potentially. We've done a lot of clinical trials at this point, and almost all of them show that it might be the case that the disease causes lower vitamin D rather than that vitamin D causes the illness. And so vitamin D has not really been shown to do anything protective, with the one exception. I mean, there's a few little exceptions. One of them is, for instance, osteoporosis. Vitamin D aids in the absorption of calcium into the body. So maybe it'll help for osteoporosis, but for almost all the diseases it's been investigated against, it has not been helpful. So therefore, I'm not very optimistic about vitamin D's protection for COVID-19, despite the correlation. But there might be, and it is currently being investigated. There are current clinical trials being undertaken. There is a problem with taking vitamin D. With a lot of these things, you have to remember, it's not just about efficacy, or there's also the safety issue. A lot of people have high cholesterol, and so there might be inflammation in the arteries because of this high cholesterol that's accumulated. And one thing that could happen if you take vitamin D, particularly at high enough doses that you might want to help for COVID-19, one of these things that you might see is that you'd have increased calcium absorption, because we know that happens with the increased calcium absorption when you have more vitamin D, and you might get more hardening of the arteries, which is a very serious illness over time if you have not just inflammation in your arteries, but then you get hardening of the arteries caused by calcium deposits in the arteries. So taking high levels of vitamin D could actually kill you over a long period of time. And so it's probably not something we want to do until more evidence comes in. All right, ask me some other questions. There's some really interesting ones out there.
Okay, so thank you for that information on vitamin D. I will use that.
No, do not use it. My point was, do not use it. There's clinical trials that are going on. Don't use it.
I'm saying I'm using that information immediately starting today. You can infer.
I'm keeping track of this. If I find that anything changes and there's new clinical trials that are released that demonstrate that vitamin D is something that we should be taking because the sum of evidence indicates that it is better for us to take than not to take. So when you balance the safety and the efficacy, I'll let you know. Right now, it's not warranted to take vitamin D for COVID-19. But spend time outside. You'll get vitamin D just by spending time outside in the summer months. Enjoy the time outside. Do not take the supplements.
Okay, good to know. Okay, so we're going to switch gears here for a moment. And Deborah Weisletter, if you can unmute yourself, has a question regarding Swiss policy info being sent out and the Forbes info. It's all yours, Deb.
So Glenn knows I have been reading a lot of articles, and before I even think about how I feel about them, I have been lately sending them to Glenn, asking him if they're legit. So Glenn, you asked me to please bring this up because apparently the two articles that Becky referred to are not as legit as they adamantly seemed. So please comment.
Yeah, so in fact, I will use this as a segue for a broader discussion on the infection fatality ratio, but it's part of the same question. So let's talk about the hierarchy of evidence. So there's a hierarchy of evidence in epidemiology. The very, very, very lowest form of evidence is expert opinion. Someone says, I believe this. And because they have an MD after their name, or they have some sort of title, then people say, oh, so-and-so says they believe this, and so let's trust it because it's useful information. An example is in terms of what you were referencing from that website, one of the claims was, I believe that lockdowns cause more harm than good. And quite a lot of physicians are saying this. In addition, I think there's some letter that's circulating with over 600 physicians who have signed on to this idea. They believe that lockdowns cause more harm than good. But the problem is, this is expert opinion. And this is the very worst source of evidence for any sum of evidence analysis. As you start going up, I'll just briefly say some of these other studies. So an in vitro study looking in the test tube. In vitro is actually glass, but now test tubes are usually not made out of glass. But anyway, in vitro is not, it's anything before an animal, but you're doing like lab science on it or bench science. An animal study is then typically a better approach than just the in vitro study that might just focus on cells, because we all know that living beings are kind of the ultimate Rube Goldberg device where there's all sorts of things going on. And so once you can do a study on animals, then you start to trigger these other possible things going on in the body, and it provides better evidence. Then you have ecologic studies, which are sort of saying, okay, this country has more tuberculosis vaccines, and the ones with more tuberculosis vaccines have less COVID-19. And so this, at a state level, you can see this relationship. You don't know what's going on at the individual level. Is it the ones who actually got the vaccine who are prevented or not? There could be something, it's just a correlation. That's an ecologic study. A cross-sectional study, also you're looking, it's observational. You might be looking at correlations between people. Then you start going up. I'm not going to go into too much detail. Randomized controlled trial, you all recognize that. That's a typical like drug trial that we're talking about, but it could be any sort of intervention where you have a treatment arm or an intervention arm, and then you also have some sort of control. And so this randomization typically is a best practice among all these other types of trials and studies. And then above that, the best form of evidence is what's called a meta-analysis of not just the randomized controlled trials, but a meta-analysis of the sum of evidence of everything that we might have. Also, it's sometimes called a systematic review. There's a little bit of difference between a meta-analysis and a systematic review, and that a systematic review tends to be a little bit more qualitative, and a meta-analysis tries to be a little bit more quantitative in terms of how the synthesis occurs. And so when you look at this in terms of a lot of these websites and what people are saying, it's all this expert opinion. They're not referring to these trials. And the problem that I'm starting to see is now they're starting to refer to trials, but they're cherry picking the ones that they do. And so let me go into, so the first thing is the website that you showed me, so, and they're proliferating all over the place, are just beliefs, and where you have people who are physicians who are saying, I believe, for whatever reason, they provide arguments of why lockdowns may cause more harm than good, but I'll get into this in a second of why we know that's not the case with real data in the United States and abroad. But first, let me jump into this issue of people who are infected. What's their rate? What's their risk of dying? So at people who are living in the New York City metro area, we have really good data on this. Why do we have good data? Let me show you some previous slides from a few weeks ago, but I just haven't updated them, but they're there. So we know how many cases there have been. These are, a case by definition is a diagnosed infection. So there are undiagnosed infections, which are either asymptomatic or people who had symptoms but just never reported it to anyone. We also have good data on the number of deaths in New York City. And now there have been more recent studies, seroprevalence studies. So what I'm using the quotes because seroprevalence is this term it's essentially an antibody study. So anytime where it's not the virus that you're looking at, it's not a report based on cases, so it's not diagnosed, but you take blood samples of the larger population to see what the spread is. And that's typically called a seroprevalence study or an antibody study, or that, again, this is what we're looking at in these areas. And so we have really good data. We know for New York City deaths, in addition, these are the reported deaths. We have even better information about, which I'll get into a second. Well, I can start talking about it here. So among the deaths in New York City, we have reported deaths, which are dark blue. You have the light blue, which are suspected deaths. And then you have the black line, which is total deaths. Let me take one step back. Well, let me finish this thought, and then I'll come back to the broader issue of excess mortality. So we know how many people have died in New York City really well. We have a really good handle on this. And based on the New York City's testing, which is widespread and ongoing, we have a really good handle on how many people have been infected in that vicinity. It's around 20% or so. Based on that, we have a really good idea that we have in New York City an infection fatality rate of approximately 0.93. And so what this means is that for every 10,000 people infected, 93 will die. Almost 1% of people who are infected will die. That was the experience in New York City. There were tens of thousands of deaths. This was massive. We know what happened in New York City with extremely high confidence. How is high confidence? Let me explain to you what this looks like, what we're looking at in this graph. So this was an example of a meta-analysis of all the sums of evidence that we had right now, looking at the infection mortality rate. So it looked at the seroprevalence studies on the one hand, so the antibodies, what's the total infection rate, and then on the other side, looking at the total death rate. You see that it varies. When you look across all of the studies around the world that have been used in this, you can see right now that the average is around 0.74. So another way of saying that is for every 10,000 people infected, 74 people will die. And so they've looked at this in different ways. One way of looking at it was grouping them by month. So for instance, if there's variation by month, then you would know, okay, well, is the infection mortality rate getting worse or getting better over time? And what they found was that there was no trend over time. That when you see, so the diamond down here is the average of all of these other ones. In February, the best estimate was around 0.47, so 0.5%. Again, 0.5 to 0.6% in March. The best estimate in April, when we started getting some really rich data coming in, was 0.9%. In May, you had some smaller studies reported. So far, it's not the end of May. It's just this was in the first week or two of May that it was reported, 0.65%. So our best estimate, rather than looking at a point estimate, is probably a range. That it's probably between 51 to 100 people will die out of every 10,000. All right, so this is our best order of magnitude understanding of what this looks like. This is a typical plot in epidemiology that you would see. The red line represents the average across everything. The diamonds are averages across the subs. It demonstrates a level of rigor and competence that was done for this study. They also evaluate it in different ways. So for instance, the approach used in the study, does modeling it versus an observational study versus preprints, does that vary a lot in terms of it? You don't want to avoid preprints because something like New York City, even though it hasn't technically been printed yet, it's not in print, things take a long time to go into print, frequently a couple of months. The New York City experience was so massive and the data is so clean that it should count for a lot for an analysis like this. And so it makes sense. One way to look at this is that you look at what are called the error bars. So the larger these lines, the less confidence we have that the point estimate is best. The point estimate is just sort of like the center measure in terms of the range, but the studies that have smaller, but that have almost no line or smaller lines, those have much more confidence. In general, it's because it's a much larger population that was investigated. So we have high confidence. We're getting recent reports. Spain had similar numbers. Their best estimate is approximately 1%. So 100 out of 10,000 people would be expected to die according to that. And so this is a serious disease. And so this has been looked at by China. Their estimate was over here. They estimated when you group all the China studies, sometimes you can't trust the data coming out of China. Their estimate was 0.67. That compares to our 0.74 really, really well. So the China data was pretty on target in terms of the numbers that we're looking at in the grand scheme of things. So now here's the problem. So this was a study that was done well. There was another study, and in New York City, we're looking at tens of thousands of people that have died in New York State, let's say. And so this is, a lot of people have died, or over 10,000. We have a big base that we're looking at. In contrast, there was this other study that was done, and my worry is that, so going back to this, it seems like a lot of people are motivated. So these people with expert opinion, they're realizing that, people don't trust random opinions. What they need is a meta-analysis. Because if they publish a meta-analysis, then people will believe them even more than expert opinion. And so what some studies have, or one in particular has done, is they've cherry-picked. If you look, let's go back here and look. You can see that the range of studies from these trials varies a lot. Here's one study that shows 0.2%. 0.2%. So an average flu season is around 0.1%. So this is not much worse. 0.2% is not much worse than an average flu season. And you see a couple of studies that have done that at 0.2. This one's coming in at 0.36, but you see that there are some that come in very low, and then there are some that come in very high. And so you have to look at the distribution and then look at the central tendency across all of the studies. And that's why we have such such confidence in this number. The problem is now there's being some that are reported and they're cherry picking just the ones that are tiny. When you look at the death rates that they're including, they're using an Iran study that was tiny. Iran almost certainly underreported their deaths because there's political motivation not to say that so many people died. So you have a tiny number of people reported. When you have a tiny number of people reported as dying, whatever the prevalence rate is, you're going to have a tiny, tiny mortality rate that's reported. Similarly, when you go down the list, these mortality rates are even less than the flu. So this is really problematic. And look at the total number of deaths that they're using here. 7 people, 300 people, 50 people. We have good data. We see New York where there's over 10,000 people. We should be using that. Do you see any numbers in here? Okay, this one, China, Wuhan, that was the only one, 0.35, but the infection has killed so many tens of thousands of people more than this at this point. This I consider diabolical, for them to exclude all the big ones and only include the small ones. And the problem is that the CDC now, the US CDC, is using estimates that they don't tell us where they're getting these estimates from, but it seems like the only place they could be getting these estimates from are either a process, either this study itself, or a process like this study where they're simply cherry picking data, totally ignoring the big ones, ignoring the ones with no error bars like New York City, in order to sort of like cherry pick these ones with tiny, tiny death rates. And it's not just malfeasance where maybe they didn't know better. Like, this is diabolical. It's terrible, because what we're seeing here is what really should be just an expert opinion in terms of the level of evidence is now being put into writing, and some people are interpreting it as almost the highest quality of evidence, when in reality it's not. It's terrible. It's rubbish, and it worries me. And so I don't know what to tell you. Ultimately, you can always ask me. I can help you to interpret this stuff if you trust me. Don't trust my word for it. I'm only an expert too in terms of interpreting this stuff. What you should do is, when we discuss the studies, I can help you to understand them and what's published and the ranges around what's published, and sort of the things that epidemiologists think about when we're interpreting these studies and trying to evaluate which are better sums of evidence for us. But it's real, the proliferation of just this nonsense, this garbage that's out there. Most people who are not epidemiologists have no good way to evaluate it. Another way, one of the other websites that you showed me, they had no bad news. I don't like to be the bearer of bad news. There's some good news in some of these reports and some bad news. But any website that only cherry picks and only shows the ones that demonstrate that everything is going great, but doesn't even mention all the ones that are showing that things are not going great, and tries to pick an average between them, you know that they're arguing. They're trying to put together an argument to convince you of something, as opposed to showing you the full range and then having you generate your own interpretation based on the data. And this is, it's problematic. Doing epidemiology requires years of training and experience and understanding, and it's not something you can do just in a couple of weeks. And it's a challenge. We need to rely on experts in terms of interpreting data if we're not going to do it ourselves. But that, again, is just expert opinion, and there's no easy way for someone who doesn't have any background in evaluating these trials to know if it's just expert opinion versus a true meta-analysis that was systematically done with rigor. I don't know. Do you have any follow-on questions, Debbie? I'm sorry. I was talking a lot.
No, thank you. But I will continue to reach out to you as my expert, because you are way more expert than anybody else I know. So thank you.
Thank you.
As will I.
Ah.
So to kind of go
We have
back.
time for one or two more questions. Let's push
Okay.
it.
Okay, so to loop back to when we were talking about the tracers, so the contacts and tracers, Sandy brought up a great point about, aren't the tracers' success contingent upon people being honest about where they've been, with whom they've been? And the same problem as the privacy issues with GPS tracing. Sandy, you went on to say, what happens if people, families starving for income, business survival, do not stay home if they were exposed or showing symptoms? How do you police that as a society? And we're seeing in salons major outbreaks by just one person showing up sick. So how can we rely on this kind of contact tracing, and what can we do to protect ourselves from that?
Yeah, there's a lot of interesting questions in there. The first thing to say is that contact tracing and testing does not need to be 100% effective for it to be effective enough. And what I mean by that is, as I've mentioned before, when the reproduction rate is above 1, then that means you get continued exponential growth at some level. The higher the R number, the faster the exponential growth. As 1 is only a little bit above, as the R factor is a little bit above 1, you still get some growth. When R falls below 1, so that is for every person who's infected, they infect on average less than one other person. So say you have 10 people infected, you might, if on average only 5 people get infected from those, then that makes the R of 0.5, and the infection will decrease over time as long as you can keep that. So if we can get, say the R is 2 over the summer months, let's say for the sake of argument 2. If contact tracing and testing is only 75% effective, so we miss 25% of the cases out there of the infections, they start their own chains of infection, 25% we miss, you can still get it down under 1 to a meaningfully small way that it's going to end the infection. Another way of saying this is, say someone goes out to work, they're minimum income, minimum wage earner, and they can't afford not to work even though they might have symptoms, they don't want to tell anyone or reveal that they're sick. That person might have a chain of infection where they infect on average 2 other people. If it's summer month, let's say 2 to 3 other people. Those 2 to 3 other people will be new opportunities to be tested and traced. And if you miss those, then there will be some others that can be tested and traced. Let's say you get 2 or 3 people down the chain who you identify, then part of the role of contact tracing will be to take the person that you identified as a positive, trace back to see who they might have gotten it from. And then once you've traced it back 1 or 2, then you can stop that whole chain there. And so again, the key point here is we don't need it to be 100% effective. It only has to be, say R is 2, it only has to be 50% effective to keep it at 1. So then it's not going to be an outbreak that grows. It'll just be maintaining the underlying infection rate. And if we get it below 1, so if it's better than 50% effective, then that's even better, and we can get it down to 0. So my point is, yes, and this it's extremely intrusive. Can you imagine? So people are going to be losing income. If people are doing illicit behavior, say drug use, and they caught it from someone they were doing illicit drugs with, or people who are having affairs, or people who are doing other behavior they don't want anyone to know about, it's going to limit the ability of contact tracers to find out who these people are. But that's always been the case for HIV, for STDs. It's a known factor that contact tracers are very familiar with and can navigate around. The type of person who goes into contact tracing tends to be a very warm, sweet person, where a lot of their power and ability comes from their ability to engage, where they engage with their hearts and with their good intentions. And so because we know the type of person that really excels at contact tracing, we know best practices here. And so I have high confidence that if we invest what needs to be invested to get the teams up to the size that they need to be, and we have enough tests, I have confidence that this can get us to where we need to be to bring our way down in preparation for the fall and winter. So that by the time we hit end of August, September, we're in really good shape. If we don't, and we still have ours at 1, and we still have continued transmission through August, then we're going to start to have to see some tough times come September. Was there anything, let me just see if there's any other big question. I hit the infection fatality rate. Oh, the one other thing, it's getting late in time, but there's one other thing I'd like to talk about that some people have had questions about, and that's excess mortality, and this question of how do we know if the lockdowns themselves aren't causing death? Can I talk about that? I think a lot of people might be interested in that. What do you think, or is it time?
A great place to end, for sure.
All right, so I will focus on this question then. How do we know the lockdowns themselves aren't causing increased death and increased illness, regardless of the COVID-19 infection? So first, let me describe to you the concept of mortality. So I won't spend too much time on this, but it's such an important point. This is such an important question that I really want to just spend a few minutes on this. I know we've gone over the hour. I apologize, but if you're interested in hearing this, then stay tuned in for just a few more minutes. All right, so when you look at the causes of death over time, you can see that there's remarkably little change from year to year. So for instance, if you're looking at the year 2000, and then you compare that to the year 2001, the number of cases of, or rather the number of causes of death is roughly the same. You see change over long periods of time, but the causes of death don't change very much from year to year. And so based on the directions, like so diseases of the heart, based on directions, you can estimate with extremely high confidence that if you know what the death rate was in 2000, then you could have with really high confidence, you could predict what the death rate will be in 2001, just based on the trajectory. There's not a lot of noise going on at the high level. And so when you add it all up, you can see that on an annual basis, there's almost no change. And when you look even seasonally, when you look from week to week, so this is all cause of death on a weekly basis. And when you look across from year to year, you see that there's not much change. It's not much noise in the system. On an individual level, no one knows for sure if they're going to live or die. People at older ages are going to be at higher risk. It's much more challenging on an individual level to predict who's going to live or die. But when you're talking about the population of the United States, for instance, of over 300 million, all the averages average out across everyone, and it is extremely consistent. And this is so consistent that epidemiologists use this as a key foundational metric for evaluating things, to look at changes over time. It's kind of like saying nutritional science, where people look at the calorie as something that would be a standard for looking at in nutritional science, like something with calories. Here, looking at all-cause mortality and excess mortality is the bread and butter. It's like the calories of looking at outbreaks. It's not a new concept for epidemiologists, although it is a new concept for non-epidemiologists. My worry is that you could invent a new metric for nutrition, like the carrot index, the number of carrots that people eat in a year. And that might be a really creative way to see if people are eating nutritiously. But it's not a standard metric in nutrition, it's creative. In epidemiology, for most people now, most non-epidemiologists don't know what the standard metrics are versus something that's just creative in terms of looking at it. All-cause mortality is not creative. All-cause mortality is one of the foundational metrics in terms of what we look at. Because it's so common, you can see that you can draw a line above the seasons, and you can see anything that goes above the line, there's still a gap. So you could even hit the line and that could be excess, but just to be a little bit conservative and not overestimate how much excess mortality there is, you can draw this line above it, and anything over that line would be excess mortality. And you see from time to time there is excess mortality. So this was flu, there's other reasons, but always the key thing is there has to be a reason. If there's excess mortality, something is going on. And so in this case, when you look here, you see COVID-19 is creating excess mortality. Let's zoom in on New York City. I brought this slide up before, but let's really take a closer look. So here we have the dark blue, which is confirmed deaths. We have light blue, which is probable deaths. And again, probable deaths are, there are insufficient tests. If someone dies, it's a dead body. You don't want to waste your test on a dead body. You want to give it to someone who's alive just because there are not enough tests. And so if someone likely died from COVID-19, then that's where these are listed, because it was pneumonia, it was something else. And there's flu, it's not flu season anymore. So people who are dying here from these flu-like illnesses, it's very unlikely to be something else. But what you see is that there's all this additional excess mortality. This is not just a creative thing. Oh, by the way, this is here. This is a foundational metric in epidemiology. And gives us extremely high confidence that these people died from COVID-19. Another way of saying this is that if these people did not die from COVID-19, then there is another outbreak of something else going on concurrently that we should know about, because there are all of these unexplained excess deaths. And so we know COVID-19 outbreak is going on. So almost certainly these excess deaths are COVID-19 deaths. All right. And so we have extremely high confidence in this as epidemiologists. Now, going back, one thing that you could say, just looking at this graph alone, well, how do we know that these excess deaths were not due to the lockdown? What if there's increased suicides? What if there's increased other illnesses where people have died because they didn't want to go to the hospital because they were afraid of getting COVID-19? They died of a heart attack at home. They did not have COVID-19. How do we know that these cases aren't due to that? And that is the key question that people are asking. And let's dive into that a little bit deeper. So if it were the case that, well, I'll just say here, so it's a hypothesis, and then let's test it with data. If it were the case that lockdowns themselves were causing increased mortality and outside of COVID-19, then you would expect that in all states in which there was lockdown, or even if there wasn't lockdown and people were afraid of going to the hospital, that there would be a bump during the same time period in excess mortality in all states that had lockdowns. You would expect this because the hypothesis is lockdowns cause death, regardless of COVID-19, all right? So now let's look at a state-by-state level. And so Nicholas Kristof was nice enough to do this for us. This was around 10 days ago, so it's a little bit dated, but if the hypothesis were true, you would have seen it. This is excess mortality by state. You see here in beige, this is New York City that we're looking at right now. The beige or the pink or whatever color this is was the reported COVID-19 tests or deaths that were reported. That corresponds to the report, let's just call them the reported COVID-19 deaths in New York City. The dark red were additional deaths that were this incremental in terms of the white, that would not have been expected, and there's no other reason to explain it unless there's some other outbreak going on, because these are a lot of other people dying. And so it demonstrates that in New York City, up to the time in which this was captured, there were over 20,000 deaths by that point, over this window of time of excess deaths. Now this question is, if there are no COVID-19, you would expect to see dark red in every single state to some extent, even if you had no beige, because there were no tested ones. And instead what you find is that there are a lot of states that are negative. So they have less deaths less all-cause mortality than you would have expected based on previous weeks, or previous years. Again, going from year to year to year, you see that it's so consistent. It is so consistent. And yet here, based on the numbers, Hawaii had less all-cause mortality than they had in previous years. Nebraska, Kansas, Arkansas, a lot of these, Rhode Island, a lot of these had less all-cause mortality. And so that means that the lockdown actually saved more lives than it might have hurt. The reasons are they were not having car accidents and going out. They were not having other types of accidents. They might have falling off ladders maybe, or other types of things if they were inside. The occupational hazards, those went down. So the flu deaths, the lockdowns prevented people from getting flu in addition to coronavirus. And so the total all-cause mortality actually went down. So this means two things. One, this is really good evidence that the lockdowns are not causing excessive deaths. Otherwise, in Hawaii, we would be seeing more all-cause mortality. But two, conversely, it also says, well, then, the deaths in New York City might have also been even higher than we thought, because people were not getting into car accidents in New York City and dying from these other things in New York City because of lockdowns. So that means that the threshold that we are using for New York City for the lockdown, maybe the threshold was too high because the actual all-cause mortality from other things was less than we thought. People weren't going and getting into car accidents. Right now, this is our best estimate. This is a really standard approach in epidemiology. And so it demonstrates two things. One, that the number of people dying is more than what is reported in almost all states in which reporting is going on. And this is not just in the US, this is global. When you look and do the same analysis at France and Spain, Britain, Sweden, all over, you see excess deaths than you would have expected, the same exact thing going on. And when you do it globally as well, you see a decrease in excess mortality or in all-cause mortality than you would have expected in some countries that were less hard hit. I think this is all I'm going to say about that. I just want to go through Italy. Look at this is the last thing. I'll just talk about Italy and then I'll stop here. So Italy, green was their reported deaths. Am I getting this right? So green is their mortality rate. So this is green is reported COVID-19 deaths. Red is the excess mortality from what you would have expected. Blue was all-cause mortality, what you'd have expected from previous years. Red, you see that there were a vast number of unreported deaths. In Italy, that was a little bit unique because they exceeded their hospital capacity. There were people who were having heart attacks, strokes, and other diseases that their lives might have been saved. But because the hospital capacity was breached, they couldn't be treated. And so they were treatable conditions that the person died. That might explain some of this. It might not just be a lack of reporting, but likely a lot of it is just simply a lack of reporting. These hospitals were overwhelmed. They were focused on treating the patients and making them, giving them life-saving therapeutics to get these people to live. And they were not focused on dead bodies after the person died to go and do testing on these dead bodies. There was no capacity to do that. And it makes sense that you'd see all this excess death. But that was one of the reasons. The very last thing I'm going to talk about here, and this will just take 2 seconds, is the lockdown. What are the reasons for the lockdown? And there were 3 reasons for the lockdown. Oh, nope, I'm not going to talk about it this week. All right, look, just give me 1 second because I think it's just an important slide if I can find it. It was after, hopefully I can find it in the next few seconds. Otherwise, oh yes, here it is. This is the last thing and I'll end on this note. So there were 3 purposes for the lockdowns. The very first one, remember, Italy was the first in the world to lock down. And they did it because their hospitals were starting to get overwhelmed. They realized they were going to get overwhelmed and they had to just lock down first northern Italy, then the rest of the country. Then other countries started started the lockdowns as well because we wanted to avoid overwhelming hospitals. It was the only way. We needed to get the outbreaks under control. That meant getting R under 1. That was the first purpose of the lockdown. The second purpose was to make sure we could get testing and tracing infrastructure set up. It took a lot of time to get enough tests ready, which we still don't have in a lot of areas, and tracing infrastructure, tracing capacity set up, which we still don't have in a lot of areas. But that was the other reason for lockdown. We needed to give ourselves time to set this up. The third thing was to reset the clock because lockdown theoretically could ultimately, if it was done well, bring R down to 0. And then by resetting the clock, you'd have such few new infections, it would be much easier for testing and tracing to track everything. And these were the 3 goals. They were extremely effective. Again, I showed you this slide previously. R has been going down. It would have been nice if R went down even faster, but for a variety of reasons, including household transmission, and people are still going out to the supermarket and still going out. So it's not a true quarantine. It was hard to get our data. But I'm going to leave it there. We'll come back next week. Thank you everyone for joining and staying in, especially for the last few minutes. I'm sorry I went over, but it's such an interesting conversation.
We appreciate your time. I don't know about everyone else, but I feel like a pseudo-epidemiologist. Now that we tested a hypothesis together, I mean, aren't we all epidemiologists? I mean, now I feel like I can really read these graphs and understand the charts that we're seeing and the data and analyzing the data with a more scientific eye. So I think I speak on behalf of the entire audience by saying thank you for the knowledge that you impart every week.
Thank you.
We appreciate you sharing your time with us. And can we expect to be together same time, same place next Sunday?
Next Sunday, 3 p.m. Eastern Standard Time. I look forward to your questions. So please think of some good ones. I look forward to answering them.
Thank you.
Thanks, everyone.
Bye, everybody. Be
Bye-bye.
well.